Alright guys, today we're going to be discussing recursion, specifically uh, for the ACSL competition. Now, an important note is that although we will be discussing it for the ACSL competition, that doesn't necessarily mean that this won't be used for much more than the competition necessarily. And in fact, recursion is a very common topic and a topic that you'll see a lot um, after or beyond rather just the competition. So just note that although this video was made with the intention of being used for the ACSL, it will be much more useful than that in the long term. A second note is that this video will be split up into two parts. In the first part, I'm going to give a quick, very simple, by no means super in-depth refresher on what recursion is for people who might not know. And in the second part, I'll be going over some practice problems and solving them so that people can understand how to solve problems that might appear in the ACSL and beyond. So in this first part, which is a very quick refresher on recursion, the big question we have to ask ourselves is, well, what is recursion? And recursive functions are functions that call themselves. This is the very simple, extremely simple definition of what recursive functions are, and admittedly, for someone who doesn't know what they are, this definition might not make a lot of sense, so hopefully I can help it make a little more sense in the coming minutes. So let's say you have a function f of x that you define as x plus 2. Now, this is a pretty standard function, and it evaluates to a real number for whatever value of x one would like to plug in. For example, if we decided to solve for f of 5, we would get the answer 7 because we'd plug 5 into x, and 5 plus 2 is 7. This is rather straightforward, and I assume at this point, if you're watching this, you should know basic math like this. Now, recursive functions are a little different, because rather than always necessarily evaluating to an answer, instead, recursive functions might call themselves. So as you can see here, this is a very simple recursive function, and we can see that whenever the value of x that we're plugging in is greater than 1, the function will call itself with a different value of x. And it's very important to note here that this is a piecewise function. That is, it has two parameters. So when x is equal to 1, this will evaluate and you will get a number. And when x is greater than 1, it will call itself again, and there's a little extra bit there, plus x. Now, I'll go over why it's super important to have a base case a little bit later. But for now, what you should understand is that it will call itself. So for example, if we wanted to evaluate f of 2, well, 2 is greater than 1, so we'd have to evaluate this first case of the piecewise function. And yet, this calls f of 1 plus 2, so we'd also have to evaluate f of 1 as well. Moving on, I'm going to go into a very simple example, and a very famous example of a recursively defined function. This is the Fibonacci sequence. That is the sequence of numbers that goes 0, 1, 1, 2, 3, 5, 8, etc. Now, as you can see here, we want to find the nth number in the Fibonacci sequence, and we can do that by using this recursive function. So for those who don't know, the nth number of the Fibonacci sequence can be found by summing the n minus 1th number and the n minus 2th number. That is the two numbers that precede it. So that's how this recursive function works. It finds the value of the number before it and the second number before it, and it sums them. Now there are a few things to note. We know that the 0th number is 0, and we say that the first number is 1. So our base case here, if n is less than or equal to 1, is n, because if n is 1, it'll be 1, and if n is 0, it'll be 0. Now, let's say we want to solve for f of 5. we could represent that via a tree, just to help us understand. So here we have f of 5. And now if we were to plug this into this equation that we have down here, we know that 5 is greater than 1. So f of 5 would actually be f of 5 minus 1 plus f of 5 minus 2. And this gives us f of 4 and f of 3. Once again, we need to evaluate what f of 4 and f of 3 are, as these don't have any concrete answers yet. So let's say we wanted to evaluate f of 3 first. F of 3, well, 3 is greater than 1, so this would be f of 3 minus 1 plus f of 3 minus 2, and this yields f of 2 and f of 1. Once again, f of 2 does not have a concrete value, so we need to evaluate f of 2 as well. F of 2, well, again, 2 is greater than 1, so f of 2 would be f of 2 minus 1 plus f of 2 minus 2, and this yields f of 1 and f of 0. Now, it's important to note here that f of 1 and f of 0 are what's known as base cases, because they actually evaluate to a number rather than calling the function again. So here, well, 1 is obviously less than or equal to 1, so there will be a value for it, and the same can be said of 0. It's very, very important to have these base cases, because if we didn't have this initial condition, and if there wasn't this second if condition here, then this would keep going on forever. If we didn't have this first condition, and we decided to call f of 1, well, this would yield f of 0 plus f of minus 1, and it would just keep calling itself over and over and over, because you would never reach a point where these base cases exist and it's evaluated, as opposed to calling itself. Now once again, f of 1 and f of 0 are the base cases, and so we can see the base cases here. The next step is to actually evaluate them so that we can travel up the tree that we've just built to ultimately find f of 5. These evaluate to 1, 0, 1, 1, 0, 1, 0, and 1, because that was defined in the function we had earlier. Now, what was also defined in the function we had earlier was that the values above each of these base cases could be found by summing the two values below them. So for example, f of 2 here could be found or evaluated by summing f of 1 plus f of 0, which we know to be 1 plus 0. Therefore, f of 2 would actually be 1. So if we were to do this for all of these, we'd end up getting this. We used the base cases that evaluated to actual numbers to solve for f of 2, and it led to 1, 1, and 1. Notice that the direction of the arrows is flipped, because before, when we were trying to simply find out what functions to call, now we have values, and we can work up this tree to find values. Moving forward, we can do this for all of these nodes on the tree to find an ultimate value of 5. This tree should illustrate two things. One, it's very, very important to have base cases. Otherwise, your tree will extend infinitely, and you'll reach what's called maximum recursion depth on your computer. That is, your computer won't let you recursively call functions anymore. And it's also just in poor taste and poor practice, because if you can't solve for something recursively, why even bother doing it? Secondly, it should show you that a general way to solve these recursion problems would be to work down to your base cases, and then using the values of those base cases, you work up to find the initial function. Here's how the Fibonacci sequence can be represented in Python. This is really just to show you how we can apply math stuff into coding. So here we say def Fibonacci, and the argument here is x, and if x is less than or equal to 1, we return x. This is the base case. And otherwise, we return Fibonacci of x minus 1 plus Fibonacci of x minus 2. And what this essentially does is represent the tree that we had in Python. Now, an important thing to note here is that virtually anything that can be represented recursively can also be represented iteratively. The reason one would choose to represent something recursively as opposed to iteratively is simply because it's elegant, it's easier to read, it's perhaps less complex, and it's easier for the coder to understand their algorithm recursively as opposed to having what may be a complicated iterative algorithm. And you can see that via this example. This code is very simple and pretty easy to understand if you actually know what you're reading and know what recursion is. Now let's move on to some problems so we can further our understanding and solidify our understanding of how recursion works, and also gain some understanding about the types of problems we'll see in the ACSL and beyond.
Alright, now we're going to be doing some sample problems of recursion that one might find in the ACSL. So these sample problems, beyond just being able to solving them will really help you understand recursion more if you didn't already understand it. So as we go along, the questions will get a little harder and a little more advanced, and we'll start with some easy ones and then gradually work our way to some more difficult ones. Here we're given a pretty simple problem. It says find f of 6, and we have f of x defined here for us. F of x is defined as f of x minus 1 plus x when x is greater than 1, and is defined as x minus 2 when x is equal to 1. So when x equals to 1, this is our base case, because clearly this one will evaluate to something. So if I can get my little marker, right, lovely. Let's work for it. So we know that f of 6, well, in this case, 6 is x, and 6 is greater than 1. So this equals f of 6 minus 1, so f of 5 plus 6, because x is 6. Now, once again, we need to evaluate f of 5, so we need to figure out what f of 5 is. F of 5, well, 5 is greater than 1, so this would be f of 5 minus 1 plus x, so this would be f of 4 plus 5, because 5 in this case is x. And once again, we need to figure out what f of 4 is, so f of 4, well, we plug it into the original equation, we get f of 4 minus 1 plus 4, and that is f of 3 plus 4. F of 3, once again, f of 3 would equal f of 2 plus 3. Let me zoom out here. Oops. F of 2 would equal, well, 2 is once again greater than 1, so it would be f of 1 plus 2. And now we need to solve for f of 1, and what do you know? 1 is equal to 1, so we've reached our base case here. So f of 1 equals, well, 1 minus 2, that equals minus 1. So now that we've achieved this answer of minus 1 here, what we can do is we can plug it back into the f of 1 here. And this yields minus 1 plus 2. So we know that f of 2 equals minus 1 plus 2, which equals 1. And once again, we can take this answer and plug it into the f of 2 here. So this equals minus 1, or apologies, just positive 1, plus 3, which equals 4. Then 4 plus 4 equals 8. 8 plus 5 equals 13. And 13 here, plug it back in, plus 6 equals 19. So your final answer is 19. All right, so we figured out the first question. Here's the second question. And what we're going to do will largely be the same as the first question. You'll notice that this question actually has two base cases where f of x is defined. When x equals 0, it evaluates to 2, and when x is less than 0, it evaluates to 5. So let's solve this one like we solved the first one. First, well, we want to find f of 2, and well, 2 is greater than 0, so this will actually evaluate to f of 2 minus 1, which is 1, f of 1 plus x, so f of 1 plus 2. Now I want to solve for f of 1, and f of 1, well, 1 again is greater than 0, so this will evaluate to f of 0 plus 1, And now we want to find f of 0, and we know that f of 0 simply is just 2. So now we can plug this 2 into this f of 0, and we will get 3. So now we know that f of 1 is equal to 3. And once again, we can plug this 3 into the first one. So we'd get 3 plus 2, which equals 5. So we worked down to the base case and then plugged in values to go up to find the final answer. Now we're going to work on this third question. And by the way, you guys can just pause the video here, try and solve it on your own, and then see if your workings match my workings and if your final answer matches my final answer. Anyways, let's try and solve this equation here. We have f of x is defined as f of x minus 64 plus 100 when s is greater than or equal to 64. We have f of x minus 8 plus 10 when x is in between 8 and 64, inclusive with 8. And we have it defined as x when x is less than 8. And we're trying to find f of 238. So here, f of 238 is what we're trying to find. And well, 238 is greater than 64, so we're doing this first case here. And this evaluates to f of, well, 238 minus 64 is 174 plus 100. And we're going to keep working down until we reach a base case, which is when x is less than 8. So f of 174, well, again, is greater than or equal to 64. So we're going to subtract 64 from 174, and we're going to get f of 110 plus 100. Here I'm going to zoom out. Whoops. Okay. And then we have f of 110 equals f of, it's greater than 64, so we're going to subtract 64 from it. F of 46 plus 100. Now f of 46, well, 46 is less than 64, so we're doing the second condition. And so we're going to subtract 8, so we'll get f of 38 here plus 10. And then once again, we're going to get f of 38. And this equals f of 30 plus 10. And f of 30 equals f of 22, my eraser. I've lost my cursor, that's not good. Right. F of 22 plus 10. And then we'll move to the side just so we can use the space more effectively. F of 22 equals f of 14 plus 10. And f of 14 equals f of 6 plus 10. Now here, we know that this f of 6 satisfies this base condition, this base case, because x in this case is less than 8. So we know that f of 6 is just going to be 6 simply. And we can plug this in to the equation of here, so we get f of 14 is actually equal to, let me zoom out again, is actually equal to 16. And this one is equal to 26. And then here we have this, or I'll do it in a different color, is equal to, well, 26 plus 10 is 36. For this one, we have 46, and then 56, and then 156, and then 256, and then 356. Because, again, we went down, and then we just plugged in values into the previous equations. Next up, we have this equation, and this equation is very interesting. because we have f of x is defined as f of x minus 2 plus 1 when x is greater than 1. And it's defined as 2 when x equals 1 and 1 when x equals 0. So here you can see it's actually calling itself twice within the function. So we're going to need to figure out how to solve that. And you would solve it very much the same way you'd solve any of the previous questions we did. You simply work down to the base cases and then work up. However, in this case, you need to work down, work up, and then work down again, and then work up again. And if that's not clear yet, it should be super clear when we solve this problem. So try it on your own and then pause the video now, try it on your own, and see if our answers match. Okay, so what we're going to do is, firstly, I'm going to zoom out just so I have a little bit more space. Lovely. And we want to find f of 6. So f of 6 is the goal. Now 6 is greater than 1, so we're going to be doing this first case. And this actually calls for f of 4 plus 1. And now the unknown here that we want to solve for is f of 4. So f of 4 is greater than 1, so we're going to use this first case, and it's going to yield us f of 2 plus 1. And once again, now we need to solve for f of 2. So f of 2, this will yield f of 0 plus 1. And we know that f of 0, well, that's just 1. So we can plug this back into that equation. So from here, we're going to get f of 1 plus 1. This is what f of 2 equals. F of 2 equals f of 0 plus 1. And because we know that f of 0 is 1, it's just f of 1 plus 1. Because we put this f of 0 back into there. We plugged it back in. Now we know that f of 1 is just 2. So we can say that f of 2 is actually 3. And that's the value of f of 2. Now, we can use this 3 and again plug it back into f of 4. So f of 4 actually equals f of 3 plus 1. The issue here is that we don't know what f of 3 is, so we need to solve for f of 3. And this is where we need to go back down to a base case. So in the side, I'm just going to move real quick. Whoops. All right. Let's solve for f of 3. F of 3, well, f of 3 is nothing but f of 1 plus 1, and it's an equal sign. And we know that f of 1 is simply 2, so this equals f of 2 plus 1. And we solved for f of 2 earlier, as you recall, that 3 down there. We know that f of 2 is 3, so if we plug that in, we get that this is equal to 3 plus 1, which equals 4. So we know that f of 3 is just 4. Go back here. All right, lovely. So this is actually just 4 plus 1, which equals 5. So f of 4 equals 5. Now we can plug this back into the above equation, so we get that f of 6 equals f of 5 plus 1. Now, just as we solved for f of 3, we will once again need to solve for f of 5. So I'll do that down below. F of 5, well, we know that 5 is greater than 1, so we'll be this first condition, f of x minus 2 plus 1. And so that will give us f of 3, plus 1 up here, not minus, if I said minus earlier. F of 3 plus 1. And once again, we've solved for f of 3 already. We know that f of 3 is 4. And so this is simply f of 4 plus 1. Now, once again, we've also solved for f of 4, and we know that it's 5 right there. So this, in fact, just equals 6. And so knowing that f of 5 is simply 6, we can plug that value back in. We get 6 plus 1, and the final answer here is 7. So what we did in this one, we solved for f of 6, we got this, then we solved for f of 4, we got this, and here the unknown is f of 2, we solved for f of 2, we got 0. We finally reached a base case, but once again, we still had a function here. This is also a base case, and then, so we got an answer here, we got an answer here, plugged it back in, and then we had another function that we had to solve, so we solved that, got an answer here, plugged it back in, and then we needed to solve f of 5. We got 6, plugged it back in, and we finally got 7 here. So it really is just working down until you reach a base case, and then working up. And then let's say you need, let's say you have another unknown or another function call that doesn't evaluate to something, then you just work back down, and then until you reach another base case, and then you work back up. And so this is an interesting problem, and is really interesting to solve and just fun to do. All right, so this is the next problem we're going to do, and this one is deceptively easy. So what we're going to do, I'm just going to move over here. Lovely. All right. So here it's asking us to find f of 2. And the function here is just a simple piecewise function. F of x equals x minus 1 when x is greater than or equal to 4, 2x when x is greater than or equal to 0 but less than 4, and 1 over x when x is less than 0. And you'll notice that this function itself, it doesn't call itself in any of these conditions. And so in fact, whatever value of x we plug in will evaluate to something. So for f of 2, this the initial function there that we want to solve, f of 2, well, 2 is in between 0 and 4, so it'd be 4. And then we'd solve for f of 4. And f of 4, well, 4 is greater than or equal to 4, so it'd give us 3. And then finally, f of 3, 3 is in between 0 and 4, so it'd be 2 times 3, which is 6. And that's the final answer. It's very simple. There's no working down and then up. It's just a pretty simple function compilation. You're just working through all these functions, finding the values, and then plugging them back in. Not necessarily as hard as some of the other ones we've been doing. Okay, this question is also very interesting because, as you can see, in this initial condition, it calls itself twice. So we will need to do a bit of math when it comes to that. But I'm not worried, and it should be fine. So I'm going to, again, zoom out real quick. All right, that should be good. Get my pencil here. All right, lovely. So here we have f of x equals 2 times f of x plus 2 in bracket minus f of x plus 1 plus 1 when x is greater than 0. We also have it evaluates to 1 when x equals 0 and evaluates to 0 when x is greater than 0. And we want to find f of minus 4. So f of minus 4, well, minus 4 is definitely less than 0. So we need to evaluate this first expression. So we get 2 times f of minus 2 minus f of minus 3 plus 1. Now, we need to evaluate both f of minus 2 and f of minus 3. But let's start with f of minus 2 first. F of minus 2. At minus 2 is definitely less than 0. So we'll need to do this first condition. So we have 2 times f of 0 minus f of minus 1 plus 1. Okay. In this one, we know that f of 0 is a base case and evaluates to 1, but we still need to find a f of minus 1. So let's do that right now. F of minus 1 equals, it's below 0, so we need to do the first condition, 2 times f of 1 minus f of 0 plus 1. Now, this is all stuff that we can evaluate because these are both base cases. So this equals 2 times 0 minus 1 plus 1, which equals 0. Now, knowing that f of minus 1 is 0, we can plug that in to solve f of minus 2. We know that f of 0 is 1, so this would be simply 2 times 1 minus 0, because we know that f of minus 1 is 0, plus 1. So 2 minus 0 plus 1, which equals 3. Now, we can plug this f of minus 2 back in here, but we still have the problem where we need to find f of minus 3. So let's solve for f of minus 3 right now. Minus 3 is below 0, so we'll need to use the first condition for this. So f of minus 3 will equal 2 times f of minus 1 minus f of minus 2 plus 1. We've solved for both f of minus 1 and f of minus 2, so this should be pretty easy to solve. We know that f of minus 1 is 0, so 2 times 0 just becomes 0. And we know that f of minus 2 is 3, so minus 3, and then we have the plus 1. This equals minus 2. So we know that f of minus 3 is minus 2. So if we know what f of minus 2 is, and we know what f of minus 3 is, we can plug both of these values back into the first equation. And make a circle. I think it looks nicer. And what we end up getting is we will get 2, apologies, I was looking at the wrong thing. We'll get 2 times 3, which is 6, minus 2 plus 1. And this is pretty easy to solve. This becomes 6 plus 2 plus 1, which equals 9, which is the final answer. Okay, so up to this point, we've really only worked on problems with single variables. But what you'll find is that a lot of problems on the ACSL and also problems in other competitions and tests will have problems with 2 variables, 2 or more variables, that is. So it's important to be able to solve these types of problems as well. And as with the problems we were solving before, it is very much the same. You work down and then you work up. However, in this case, there's 2 variables. So here we have f of xy equals f of x minus 2, y plus 1, minus 1, when x is greater than y. It equals 3 plus f of 2x plus 1, y plus 2, when x equals y, and y plus x squared when x is less than y. So this last condition is the base case. So here, let's try and solve f of 10, 4. F of 10, 4. Well, in this case, x is clearly greater than y, so we'll need to use this first condition. And this gives us f of 8, 5, minus 1. Okay, and then from here, well, x is still greater than y, so we need to evaluate f of 8, 5. And that will yield f of 6, f of 6, 6, minus 1. So f of 6, 6, well, 6 and 6 are equal, so we'll need to do the second condition. F of 6, 6 equals f of 13, 8, plus the 3. I moved the f in front of the 3 just so it looks a little better, it's easier to understand as well. Now, once again, 13 is greater than 8, so we'll need to use the first condition. So f of 13, 8 equals f of 11, 9, minus 1. And we'll do that once again as well. F of 11, 9 equals f of 9, 10, minus 1. And here, well, x is less than y in this case when solving for f of 9, 10. So f of 9, 10. We'll use this third condition, which is the base case. And this is y plus x squared. So this will be 10 plus 81, which equals 91. And then from here, again, we can just go work our way back to the top and plug everything in. So knowing that f of 9, 10 is 91, we know that f of 11, 9 is 90. This one is 89. This one is 92. This one is 91, and this one is 90. And 90 is our final answer. What you'll also find a lot of the time in these competitions is that they'll also give you their own functions. And this doesn't really change too much. It's just more math that you need to do. And more often than not, it's not too difficult. So let's solve this one as well. All right. This one, we have f of xy equals 2 plus f of, in bracket, x over 3, in bracket, y over 2 if x is greater than y. And we have the base case in any other case, which is x squared plus y squared. And they give us what the square bracket is. This is basically just floor division because it returns the greatest integer less than or equal to z. So it rounds down. So it's floor division. In this case, at least. So let's try and solve for f of 50, 18. All right, well, clearly 50 is greater than 18, so we'll need to do this first condition. 50 over 3 is 16 point something, and so we're going to round down, so we'll call it f of 16, and then 9, sorry. What am I talking about? 18 over 2, well, that's 9, so we know that this will be f of 69, and then we can't forget the plus 2 either. Once again, f of 69, x is greater than y, so we'll need to do that again. So f of 69, well, this equals f of 5, 4, because 16 over 3 is 5 point something, so you round down and you get 5. Then 9 over 2 is 4.5, you round down and get 4. And then once again, we can't forget the plus 2. Once again, 5 is greater than 4, so we need to do this first case again. And this will yield f of 1, 2. Because 5 over 3 is 1 point something, so you round down. And 4 over 2 is 2, so there's no need to round at all. And once again, you can't forget the plus 2. And now for f of 1, 2, this is the base case because x in this case is not greater than y. So we'll just solve x squared plus y squared, and this will give us 1 plus 4, which equals 5. And then once again, we can work our way up. So 5 plus 2 is 7, 7 plus 2 is 9, 9 plus 2 is 11, and 11 is our final answer. That essentially concludes all of the questions I'll be going through today. Note that I did not write these questions myself. I found them online, and I'll link to where I found them in the description of this video. Additionally, you can find way more questions to practice with online, and if your school has resources, great, use them, because really the only way to get better is just to practice. And as you get really good, you'll be able to just run through this super quickly, and you might even reach a point where you don't need to write all the steps and you can just sort of do it very fast. So just keep practicing. I'll link some more questions where I found these questions in the description, and also you can find a bunch more online. So cool. Thank you for taking your time out to watch this video. I hope you learned something. I hope you had fun doing so. Thank you and have a great day.